this computer, and then I will share my screen. Okay. Oh yeah, I was looking at a good picture for a Galton board, and you've probably seen it in like museums for science for kids, where you drop something on the top and there's a nails, some pins, and it can go left, right on any level, and as a result, you'll get distribution like a normal distribution. Okay, because this is actually related to the theme of our today's lecture, and it will be about distributions and a little bit about history of statistics. I want to show those four people. They all are from England, and they all are very famous. So Sir Francis Galton, of course, he's the one who invented the Galton board, which you just have seen. Carl Pearson, absolutely amazing guy. So 600 scientific papers and books, 400 in statistics. He actually was the founder of the statistics department in the University College in London until 1930s, when he died, and he was then substituted by Ronald Fisher. If you've heard about analysis of variance, ANOVA, or Fisher distribution, so this is him. And William Seeley Gossett, he's known by the pseudonym Student. And he's the author of the student distribution. He actually worked in Carl Pearson lab. So I would presume that mostly it's the work of Carl Pearson's, not student himself. But anyway, returning to today's topic, we'll first talk about the binomial distribution. And binomial distribution comes from a very simple process. So imagine that time is discrete, and on every step, you can go either left or right, and you have probability, or like you answering yes or no, right, whatever, left or right. And you have probability P to do one, or like 1 minus P to do another. So for example, left or right. And if this is a random process, like the question is, where will you be after n steps? And you will come to this famous formula, which is again very simple to understand. This is if P is probability to go into one direction and Q in another, and suppose that you made X steps to the right, then you made n minus X steps to the left. And this C of n to X is a number of combinations to get X and n minus X. So this will be like a share of like probability to get to this combination, right? And so this will be probability from n steps to get X. So in other words, if you look at this Galton board, and you wonder what is the probability of like after whatever so many balls you had to get X here, right? So it will be given by this this formula. I don't remember if we covered, I think we covered it on the last lecture, how you actually count all the different combinations and how you come up with this formula. Another way to think about it is this famous Pascal triangle. So you start here and you can go left or right. And then from this, you can go left or right. And from this, you go left or right. So here you have two ways to get to this point. So its share will be 2. So it's 1, 2, 1, and then 1, 3, 3, 1, and so on. So these are called binomial coefficients. And they actually, this formula calculates them. So this is just another way to think about it. And if you get bigger, 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 you'll get to this kind of distribution. Okay, so this is a simple binomial distribution. And you already see that as numbers gets bigger and bigger and bigger, the shape it takes, it becomes close to this famous bell shape or normal distribution, and this actually mathematically can be proven very easily. Okay, so if P and Q are equal, then the distribution will be centered around 0. So the expected value will be 0, and the variance or like squared error will be NPQ, which is, well, n divided by 4 approximately, right? And we will not go into mathematics of this. If P and Q are not equal, then over time, let's say P is bigger than Q, then let's say P is stepping to the right. So you will be going left and right, but you will have some drift towards the right because P is bigger than Q, and the average distance you will come in n steps will be n times P. Okay. De Moivre-Laplace theorem. At large numbers, the binomial distribution may approach normal Gaussian curve with the following parameters, and I didn't put the parameters. Whatever. Bernoulli distribution. Well, Bernoulli distribution is a very simple distribution. Here it is, 0 or 1, right? That's the famous Bernoulli distribution. So if you repeat the same experiment multiple times, so for example, you're tossing a coin, and then if the probabilities will be the same, like 0.5 and 0.5, so then the Bernoulli distribution will be simply like two columns with the same height, right? So it's not a complicated thing. People use the words and they named by, like in this case, Bernoulli, a very famous mathematician. Anyway, so this is something very, very simple. Okay, here are some formulas. So one formula, if you will decide to approximate the binomial distribution, and you already seen this formula, at large n, you can approximate it with the formula for normal distribution. Using this Stirling formula to approximate n factorial. And well, yeah, so this is, well, you've seen it on Galton board. It's kind of natural happening, but mathematically you can prove it that this is this. And from this, by the way, you can calculate this coefficient, which people usually have no idea how to calculate it. And so this is the mean value, and NPQ is the sigma squared. It's a variance, right? So you will see it multiple times throughout these lectures. Okay, Poisson distribution. Well, we haven't covered Poisson distribution. So Poisson distribution is, for example, you're sitting next to the road, and in every minute, several cars are passing, and you want to see the distribution of number of cars per unit of time. So 1 minute only 2 cars, another minute 10 cars, or whatever. You make a histogram, and the mathematical question is what will be the mathematical distribution if all the cars are independent, and that's what Poisson distribution is. And you can actually derive Poisson distribution from Gaussian distribution, well, given that the number of cars per unit of time stays the same. Okay, we will not go through this derivation. You can maybe take it on your own time. It's not difficult. And vice versa, from Poisson distribution, you can go into Gauss. But we haven't counted Poisson distribution yet, so this is, I guess, just for reference on one page. Coin tossing. Okay, this is actually interesting. So we're tossing a fair coin, and let's say tail is 0 and head is 1, and probabilities of either side is 1/2. So expected value because it's 0 and 1. So it's not minus 1 and 1. It's 0 and 1. So expected value Pn is n divided by 2, right? For large n, we approximate with the Gauss. The variance is npq. Again, this is what I was showing here. So it's n divided by 4. Standard error is the square root of this formula. So it will be square root of n divided by 2. Relative error, so we divide by the number of events. It's 1 over square root of n. And now it's getting interesting. So if we want error of 1%, we need to do approximately 10,000 tosses. So this is just a good way to estimate things. Okay, chi-squared calculations, it's premature because it's in some other lectures for the down the road. Okay, but this formula, 1 divided by square root of n, to estimate the error, it's actually very, very common. It's like a rule of thumb. I use it all the time. So here, checking whether a coin is fair. Well, if you study statistics formally, there is a chapter on hypothesis testing. So you usually have null hypothesis. So our null hypothesis will be that the coin is fair, so that heads and tails are evenly distributed, and alternative that the coin is not fair, right? So for example, we tossed a coin 10 times and got 8 heads. Compute the p-value. Again, we haven't covered actually what p-value is. It's kind of like a probability of getting event that extreme or even more extreme. So if we got 8 heads, well, it's like you would, on average, you would think it will be 5 and 5, right, from 10. But you got 8, which is shifted quite far from the average 5. And even more extreme will be 9 and 10. So you want to calculate probability of 8, 9, and 10, sum them together, and this will be your p-value. So probability of getting result this extreme or even more extreme, right? So we need to calculate probability of p of 8, p of 9, and p of 10, and sum them together. The way to do it, well, you can simply use this formula to calculate the probabilities for x, like n will be 10 and x will be 8, 9, and 10. So you'll calculate those and sum them together, right? And here we have this calculation, and we'll get 0.055. So it's a little bit more than 5%. For whatever reason, usually people like to use 5%, like it's common. So if it is less than 5%, then it means extreme, and we beyond like the error. So then we reject the null hypothesis. But here, because we, well, by a little bit, but we within the borders, we say, okay, the null hypothesis still holds. So coin flipping leads to a binomial distribution, which can be approximated with normal Gaussian distribution. Here, the confidence level for Z standard normal distribution with sigma equal 1. So what's interesting here is 1 sigma gives us about 68%, 2 sigmas 95%, and 3 sigmas 99.7%. So these are the areas for 1 sigma, 2 sigma, or 3 sigma, or Z, 2Z, and 3Z, right? Whatever. It's some conversation about binomial and normal distribution areas. Okay, how many times should we flip a coin to test the null hypothesis, right? So suppose we flipped n times and got x heads. So the estimate of probability of heads is x divided by n. Okay, and suppose x follows binomial distribution with probability p heads. At large n, it is approximated with normal distribution, which again, this e to minus x squared divided by this npq over and over again. You will see it. This is the variance of binomial distribution, npq. Okay, so we use character sigma to denote the standard error of estimating x. So npq is sigma squared. Okay, know that it has max value when p and q are the same. They're all 5. So maximum sigma squared is n divided by 4. So we can estimate the error as approximately square root of n divided by 2. And we already seen this formula before. Okay, this is very easy to remember. Error grows as square root of n, right? If we estimate error for ratio x divided by n, well, we divide it by n, we get this value. As n grows, the distribution becomes more and more narrow because, well, this thing becomes smaller and smaller. We express error e for ratio x divided by n in terms of z, number of sigmas. And here are some examples for confidence intervals. So for example, if we want error in terms of z to be 0.5, so 4 flips is enough. 1/4, 16 flips, 100th, we need almost 10,000 flips. Actually, I went through this too fast, but I don't want to get stuck on math because it's like individual thing. If you want, I recommend it to spend more time on this page and understand these calculations, kind of internalize them. Okay, if you using Python, you can use convenient modules to do all these calculations. And here are some examples. We're flipping the coin, and like we can calculate the results, or you can do just for loops to do the same thing. Here, I'm using Scifi stats, and again, this is binomial distribution. And this rectangle I just draw by hand just to show where the sigma is, one sigma. Okay, here we do a chi-square test to check where the coin is fair. And here we're doing t-test, student t-test, to do the same test. Okay, I will not go through this now because we haven't covered chi-square test or t-tests, but in real life, you can use either one of them or some other tests. Okay, so I want to proceed with some other distributions because we still have more time. Okay, so this we already covered, right? Bernoulli distribution. A little bit more about combinatorics. So let's say we have n objects or n element unordered set. Question: in how many ways can we rearrange them? And answer is n factorial. And this is very easy to understand, right? So the first element we can select n ways. The next one n minus 1 way, and so on. So we end up like if we have 5 elements, it will be 5 times 4 times 3. So it's just 5 factorial, right? Now, different question. It's about subsets. In how many ways can we select m elements out of n elements? And we don't care about the order, right? And the answer is C is of m from n, right? So it's n factorial divided by m factorial n minus m factorial. And explanation is kind of similar, right? So we need, let's say n is a big number and m is smaller number. So the first element, we can, we have n variants to select the first one, n minus 1 to the second one, and so on, n minus m plus 1 for the mth element, right? So multiplying them, we'll get a number of combinations. But then we said we don't care about the order. And the order will be m factorial. So we divide by m factorial. And this n minus 1, n minus, and so on, we can present it as n factorial divided by n minus m factorial. Because we take the full factorial, but we only need the first m elements, largest one. So we remove the rest by dividing by these elements. So this is a very famous formula, and this is a binomial coefficient or Newton coefficients. Okay. Okay, so these are subsets. Poisson and exponential distribution. Okay, suppose you're sitting near the road, you notice that on average you see 10 cars passing by every minute. So we say that the rate, usually people use lambda character, is 10 per 1 minute. So knowing the average rate, what would be the probability of having only 5 cars in 1 minute or 15 cars? And you end up having a curve like that, depending on the lambda. So if lambda is like 1 per minute, it's about this, 4 like this, 10. And you see, as lambda gets bigger, the curve becomes closer to Gaussian. And that's, remember we had, I showed the formula that you can calculate Poisson from Gaussian and vice versa at big numbers. And that's what I meant. And so if you just look at this portion, it looks like Gaussian distribution. If on average you get a lot of cars, let's say 10, 20, 30, right? So what's the probability to get 0? It will be almost 0, right? You have a lot of cars. Let's say it's a big, busy highway. So you'll always be somewhere here. And the distribution will be about normal, close to the average. Okay. So Poisson probability is the probability of a given number of events occurring into a fixed interval of time. If these events occur with a known average rate and independently of each other and of the time since the previous events. So Poisson formula is this. So lambda is the rate, how many per minute or per second or whatever. X is this X of the distribution, right? And yeah, so this is the formula, and well, you can derive it. It is derived in all textbooks, so we will not actually do that. Another interesting fact, intervals between Poisson events distributed exponentially. If we have events happening which follow Poisson distribution, we can measure the time intervals between these events and make histogram, and you will see that it will be like a decaying exponent. These times have exponential distribution with probability density looking like this: lambda times exponent of minus lambda t. This is a very interesting fact. The average time interval will be 1 divided by lambda. Standard deviation happens to be the same. I probably need a picture to show this. Okay. Uniform and normal distribution. Well, uniform distribution is, suppose you have some interval where your variable can have any value with the same distribution, with the same probability. So the probability is uniform. It's the same on the whole range. So this is a uniform distribution. Normal Gaussian bell-shaped distribution, we already spoke about it a little bit. Central limit theorem, I spoke about it last time. So the normal distribution is very common in nature, because when you have big number of sets of variables, the distribution of parameters of these sets, for example, averages, tend to converge to Bell form, and it's called central limit theorem. So suppose we have n1 sets, and each set has n2 values. All values are drawn from the same distribution. The shape of the distribution may be anything: uniform, bell-shaped, triangular, exponential, like Bernoulli, like only two values, doesn't matter. We calculate an average in each set. So we have N1 averages, and then we will see the distribution of those averages will converge to bell shape, to normal distribution. Usually when you have numbers of 30 or more, the way mathematics works, that you already see this normal shape. Okay. This is more about the central. So here we, again, we have sample groups. In each group, we calculate the average, and then we plot the averages. So here, for example, we toss a coin, and we have -1 and 1. In each of those groups, we have those two bars, but they may have different height. But when we calculate the average, it will be close to 0. And then when we make histograms of these values, like for each group, we have a value, and we make histograms of them, we'll get bell-shaped. So this is central limit theorem in action. You can very easily in Python, like in Jupyter Notebook, make this experiment. Just make a for loop or for loop and see how it works. Okay, the formula for this curve is this. So square root of 2 pi e to minus x squared minus mu. So mu is a shift. So you can shift it left or right to the value of mu. So this is just shift in x. Sigma is the width of this curve. So if it is 1, then sigma is just 1, and the formula becomes much simpler, right? It's called standard deviation. So you have here two magic variables. Pi is, you know, from geometry, 3.14159, whatever. And E comes from compound interest, and it's 2.71828, and so on. I added this page recently to explain what number E is, the Euler number. Because for some reason in like America, people don't know what it is and where it's coming from. But here is a very simple experiment. So if you invest $100 at 100% per year, then at the end of the year, you will have $200. So your total growth from 1 to 2. Now, suppose you split the year in two halves, and in first half, investment grew by 50%, and then you reinvested, right? So in first half, you grew by 50%, and then in the second half, it also grows by 50%. So together, because of this compounding effect, you get 2.25. Oh, you say, I like it. Let's split it in monthly periods. So now n is 12, and you get 1 plus 1, 12 times again. Like now you have 12 terms. You multiply them, and you get this number. You see, it's even bigger. So you say, okay, let's do it daily, and you do daily. So you do 1 divided by 1 divided by 365 to the power of 365, right? And it will be 2.7 something. If you split even further into hours and minutes or seconds or whatever, it will get closer and closer to this magic number. And this is number E. So this is the maximum you can get for your investment. And it was this problem was first solved by Jacob Bernoulli a long time ago. So 1683. Oh gosh. So it was 300 something years ago. And that's where E is coming from. And then famous mathematician Euler, he's Swiss, but actually for 30 years he lived and worked in Russia. He came up with this formula. This is like a famous factorial infinite sum to calculate E. So this is actually equivalent to this formula. And this magic number is named after Euler. So that's why it's called Euler number. Anyway, how to test if distribution is normal or not? Because distribution can be skewed, or like, for example, here you have something which looks like more as uniform distribution, right? So given the actual histogram and given like you think it's normal distribution, how you calculate the error. And well, there are different ways to do it. Again, I will not go into this. The best test is supposed to be a Shapiro-Wilk test, and it's available in Python modules. So here you can do the test in just few lines of code. Okay, the matching problem. Okay, we will not go through this, but whatever. This PowerPoints, they are on my GitHub, so you can like look at your own time. This is okay. This page, oh, we already seen it before in the previous slide deck. Gamma function and distribution. This is very, very important. Also, it is intimidating, but actually it's not intimidating. It's very, very simple. So the gamma distribution is a very simple idea. So it is simply time required for k events to occur in a Poisson process with mean arrival time of theta. So for example, if cars are passing by every 10 seconds, how long you will need to wait to get 10 cars, right? And it may be 10 cars, so it may be different. So there are two parameters. The rate with which cars are coming and how many you want to get, right? And depending on these two numbers, you will get different shapes of these distributions. And again, when numbers gets bigger, it becomes closer to the regular bell shape, right? There is absolutely nothing magical about it. And again, you see people who were inventing these formulas and the same people, right? Well, it's not Jacob, it's Daniel Bernoulli. But Bernoulli had 6 or 7 or 8 mathematicians, I don't remember, like over the years. It's a famous family of mathematicians. And Euler, again. The formula looks intimidating. It uses this gamma function, but a gamma function is actually factorial. It's a very simple thing. So gamma of n is simply n minus 1 factorial, right? And this is for integer n. And then you think, well, what if I want to define this function for any n, not just integer? And you come up with this formula. Well, not you, them, like many years ago. So if z here is integer, you will start taking this integral by parts. So you move exponent under d, then you revert it, like, you know, integrating by parts. Yeah, it's coming from calculus, and eventually you will get to this n minus 1 factorial. And then this is yet another thing. So you started with integer, then you said for real numbers, and then you said, what about imaginary, like complex numbers? And then you'll get to gamma function in complex numbers. So this is some pictures from the internet I put here. But anyway, gamma distribution is a very, very simple idea. Time required to see whatever 10 cars passing, or whatever, buses or something like that, and just what the distribution will be. Okay, actually gamma distribution derivation. Oh, okay. Anyway, you can maybe look at it at your own time. There is a link here which explains it in detail. Beta distribution, frankly, never had to deal with it. So it's similar to binomial, but in binomial, the probability is a parameter. In beta, the probability is a random variable. It has 2 parameters, and again, I guess let's not look at it. It's beyond my very, very simple lectures. Okay, and another thing to cover is moments of probability distribution. So far, we looked at probability distribution like normal, which is symmetrical and very simple. But what if it is skewed left or right? Or what if it is has this kurtosis So his, for example, we have normal distribution, and its kurtosis is 3, but it may, for some other distribution, it may be greater or it may be smaller, right? So different shapes. And there are parameters which are called the moments of the probability distribution, which are defined like this or like this, depending on whether it's discrete or continuous. And you just change the number n here. So it may be like n equal 1, it will be average, right? And 2, it will be error, and 3 will be skewness, and 4 will be kurtosis. So these are the moments. So you have moments like this, and you have central moments where you subtract the average number. But again, people use them, so you can collate the moments to estimate the skewness or kurtosis, kind of the shape of the distribution. Okay, I'm done with this second PowerPoint, and this covers it for today. I just want to remind that all the slides I'm covering, there'll be 17 of them. They're all on GitHub in my repository called Statistics. Let me stop sharing and stop